Welcome to the deep dive. Today, we're going to dive into a really tricky operational challenge. It's something anyone running a big AI model marketplace faces.
Yeah, think about places like Hugging Face or maybe Alibaba Cloud's Model Studio. You've got literally thousands of LLMs available.
But here's the kicker. Only a very small number actually get hammered with requests.
Exactly, and that creates this fundamental resource problem because if you have this huge menu of models, well, requests for most of them are just super sporadic.
Sporadic is putting it mildly.
Yeah, I mean, our sources are saying something like 94.1% of models across these big markets are invoked so rarely they're basically just sitting there idle.
That level of inefficiency is just mind-blowing. To keep those rarely used models ready, companies have to dedicate hardware, and the cost is brutal.
Oh, absolutely. We're talking about allocating, get this, 17.7% of all their GPUs
17%.
just to serve models that in total only handle about 1.35% of the requests. It's prime computing power, essentially, like you said, taking a nap.
So clearly, something needs to change. We need effective GPU pooling, some way to share these expensive resources much better.
We need to share them across dozens, maybe hundreds of different models, many with sparse workloads. The goal is to get the kind of efficiency you see when serving just one really popular model, but apply that across the whole marketplace.
And the research we're looking at proposes a pretty radical solution for this. It's a system called Aegaeon.
Mm.
And instead of just waiting for a whole request to finish, this system does its auto-scaling. Well, down to the token level, the absolute smallest unit.
It's a totally different way of thinking about resource management. You move control from the entire request, which can take seconds, down to the individual token.
Tiny increments.
Exactly. And by doing that, Aegaeon promises to really shake up how cloud resources get provisioned. The headline number they're claiming is what, an 82% reduction in GPU needs in production?
An 82% reduction.
Yeah.
Okay, that's huge. We definitely need to unpack this. So maybe let's start with the basics just to level set. What happens when you actually talk to an LLM? Because understanding that really shows why the old methods fail.
Right. So any LLM inference request basically has two main phases.
Okay.
First is the prefill phase. That's where the model takes in your whole input prompt, everything you typed. This part usually takes the most time.
Got it. Processing the input.
Then comes the decoding phase. This is where the model generates the response, token by token, auto-regressively, one word or part of a word at a time.
And for users, what matters are the service level objectives, the SLOs. These define what counts as good performance.
Precisely. For prefill, the key metric is TTFT, time to first token. How fast does that response start appearing?
Right, that first sign of life.
And then for decoding, it's TDT, time between tokens. Once it starts talking, how fast are the words coming out? Smoothness, basically. You measure success by hitting those time targets.
Okay, so now let's look at the existing ways people try to pool GPUs. They hit some hard walls. First, there's multiplexing.
Yeah, multiplexing is just cramming several different models onto the same GPU at the same time.
Not simple enough.
It is, but it's really limited by the GPU's memory, the VRAM. Even with a big 80 GBB GPU, you might only fit 2, maybe 3 large models.
Which is nowhere near enough if you have hundreds of models in your marketplace.
Exactly. For that kind of scale, multiplexing just doesn't solve the efficiency problem. You still end up with a ton of waste.
Okay, so multiplexing is out. That led people to try request-level auto-scaling. This is common in serverless setups.
Right. The idea is a request comes in for Model X, you spin up resources for Model X. When that request finishes, you spin them down.
Seems logical. But the sources point at a really critical flaw here. They call it the head-of-line blocking trap, or HOL blocking.
Yeah, and what's really interesting is why this happens with LLMs. It's because, unlike, say, a quick database lookup, LLM requests take a long time to complete.
How long are we talking?
Well, the research we looked at found the average service time was around 16.79 seconds. Let's call it 17 seconds.
Wow, 17 seconds for just one request to finish. So the model is busy for that whole time.
That's how the request level scaling sees it, yes. It assumes the model and its resources are needed for that entire 17 seconds.
Okay.
And the numbers this leads to are pretty stark. Even with a really low overall arrival rate, like 3.7 requests per second spread across 100 different models, the math shows you'd expect about 46 or 47 models to be active at any given moment.
Almost half the models are considered busy just because they're somewhere in the middle of processing one of those long requests.
Exactly. So if a new request comes in for Model A, but Model A is already working on that 17-second request, well, the new one just has to wait. That's the head-of-line block.
Ah, I see. It's like being stuck in line behind someone doing a really complex transaction.
Perfect analogy. The person behind you might just need a quick withdrawal, takes 1 second, but they're stuck waiting for the 17-minute loan application ahead of them to finish.
And the consequence is you can't really pool effectively. You still end up needing almost one dedicated GPU per active model, even if it's only handling one long request.
Pretty much defeats the purpose. You're almost back to needing dedicated resources, which is what we wanted to avoid.
Right. Okay, so that's a dead end too.
Hmm.
But if requests inherently take 17 seconds, how does Aegaeon possibly break this HOL blocking? Switching models sounds like it would add more time, not less. Doesn't the overhead kill you?
That is the absolute key to Aegeon. They realize they don't have to wait the full 17 seconds.
Ow.
Because decoding happens token by token, and between generating one token and the next, there's a tiny, tiny pause. Milliseconds. Aegeon jumps in then. It does preemptive auto-scaling at the token granularity.
Wait, so you're saying in the little gap between generating, say, token 5 and token 6 for my request, Aegeon could pause my request, load up a different model, generate a token for someone else's request, then switch back to mine to generate token 6, all without me noticing a delay.
That's exactly the idea. They exploit something called slack time. Remember the TBT, time between tokens?
Yeah, the speed of the stream. Maybe 100 milliseconds for a good chat experience.
Right. But actually generating the next token might only take, say, 30 milliseconds on the GPU. That leaves 70 milliseconds of slack.
A buffer.
Precisely. That 70 milliseconds is gold. It's the window Aegeon uses to quickly swap the current model state out of the GPU, swap the pending model state in, do a quick bit of work, and swap back, token-level context switching.
Okay, that sounds incredibly complex to manage, all those rapid swaps.
Yeah.
How do they schedule that without creating chaos?
Good question. They use something called disaggregated scheduling. Basically, they split their pool of GPUs into two specialized groups.
Okay.
You have prefill instances, which just handle that initial prompt processing.
Yeah.
And you have decoding instances, which just handle the token-by-token generation.
Why split them?
Because the workloads are really different. Prefill is bursty. It can suddenly demand a lot of computation for a short time. Decoding is more like a long, steady marathon.
Ah, so mixing them would be bad.
Yeah.
A big pre-fill job could interrupt everyone's ongoing chats.
Exactly. By separating them, they can keep the decoding stream stable and predictable while still handling the lumpy prefill work efficiently in its own partition.
Makes sense. So what kind of scheduling policies do they use within these partitions? For pre-fill, they use something called grouped first-come, first-serve. Why the grouped part?
It's all about minimizing overhead. The act of scaling up a model, loading its weights, getting the engine ready, that takes time. It can actually be comparable to the time it takes to run a short prefill job.
So if you scaled up for every single tiny request...
You'd spend all your time just setting things up and tearing them down. Huge waste. So Aegeon groups incoming requests for the same model together up to a certain batch size, like 8 requests.
Okay.
They load the model once, process that group of 8 requests, and then scale it down. It drastically reduces the number of expensive scale-up operations while still basically following the first-come, first-serve order for fairness.
Clever. Batching the setup cost. And what about the decoding instances? How do they manage the scheduling there? You mentioned the slack time.
Right. For decoding, they use a weighted round-robin approach. It leans heavily on that slack time concept.
How does the weighting work?
The scheduler constantly tracks how close each active decoding request is to missing its TBT deadline, its SLO.
Okay.
If a request has plenty of slack time, meaning it's way ahead of its deadline, it gets a smaller time slice, a smaller quota on the GPU in the next round-robin cycle.
Letting other, maybe more urgent requests get a turn.
Exactly. But if a request is getting close to its deadline, maybe falling behind, it gets a larger time quota to help it catch up. It's dynamic, constantly adjusting to maximize GPU sharing by using up that available buffer time without actually hurting the user experience.
This whole token-level switching thing sounds amazing on paper, but it really hinges on being able to swap models in and out incredibly fast. You said sub-second.
Absolutely. If scaling took seconds, like it traditionally does, this whole token-level idea would be completely impractical. Pure fantasy, as you said.
So how did they achieve that? The sources mention a 97% reduction in the auto-scaling overhead. That's almost unbelievable. How do they pull that technical miracle off?
It really is the engineering heart of Aegeon. That 97% optimization is what makes the whole system feasible. An unoptimized switch, like for a 13 billion parameter model, could genuinely take almost 27 seconds.
Okay, so what did they optimize?
They tackled three main bottlenecks. The first was component reuse.
Opponent reuse.
Yeah, they figured out that a lot of the delay came from initializing complex background systems every single time they switched models. Think about the distributed computing frameworks like Ray or NCCL that manage parallelism. Setting those up from scratch takes
It's
ages.
like rebooting your whole computer just to open a different app.
Exactly. So Aegaeon initializes these core inference engine workers just once when they start up. It keeps the heavy, complex stuff, the executor, the communication libraries cached and ready. Then it just reuses them when switching models.
Like putting the engine in standby instead of a cold start.
Precisely. That step alone cut out over 80% of the initial startup latency for a switch. Huge win.
Wow. Okay, so that's one big chunk. What was the second obstacle? Memory management. You mentioned fragmentation being an issue.
Right. Memory is always a headache. They had to optimize both the GPU memory, VRAM, and the regular host memory, DRAM.
Let's start with VRAM. That's where the model weights and the active KV cache live, right?
Correct. The standard way libraries manage GPU memory can lead to fragmentation, where memory gets broken into small, unusable chunks. Cleaning that up requires garbage collection, which is slow.
Okay.
So Aeon basically bypasses the standard allocator for its critical data. It uses a technique called bump allocation. Within a large pre-allocated buffer, it manages itself.
Bump allocation.
Think of it like just using memory sequentially from the start of the buffer. When they need to clear space for a new model, instead of complex garbage collection, they just reset a pointer back to the beginning of the used section. Bang! Instant memory reclamation. Super fast, no fragmentation within their buffer.
They built their own little memory sandbox.
Essentially, yes. And for DRAM, the host memory, they faced a different challenge. They need to store the KV cache states for potentially hundreds of inactive models waiting to be swapped back in.
And those KV caches can have totally different sizes and shapes depending on the model, right?
Yeah.
Like a 7B parameter model versus a 72B one.
Exactly. If you just allocate and free that naively in DRAM, you get massive fragmentation pretty quickly. So here they use another technique called slab allocation.
Slab allocation.
It's a known method for managing memory efficiently when you have objects of varying but somewhat predictable sizes. They create pools or slabs of memory chunks pre-sized for common KV cache shapes. It minimizes wasted space and fragmentation when juggling all those different states.
So specialized buckets for different cache sizes.
You got it. Combine that with also caching the model weights themselves and even having the ability to pre-fetch the model they think will be needed next into a separate queue. Well, the actual scale-up time when a model needs to become active on a decoding instance becomes almost zero.
Okay, that's VRAM and DRAM. What was the third optimization? Something about synchronization.
Yes, fine-grained KV cache synchronization. All this data juggling, moving KV caches between the host DRAM and the GPU VRAM involves I/O operations, swapping data back and forth.
And you don't want the GPU sitting idle waiting for that data transfer to finish.
Precisely, that would kill performance. So Aegaeon uses very specific low-level CUDA commands, basically like little flags or signals called CUDA events. They use CUDA event record and CUDA stream wait event.
Okay, technical, but what do they do?
They allow the system to track the progress of each individual memory transfer very precisely. Is this chunk done moving? Is that one still going? By knowing the exact state, Aegaeon can intelligently overlap the data transfers, the swap in and swap out, with actual computation on the GPU.
So the GPU keeps working on one model while the data for the next model is arriving in the background.
Exactly. It hides the latency of the memory swap behind useful work, minimizing the synchronization overhead. The GPU is always busy.
So it's these three things together. Component reuse, that explicit VRAM-DRAM management with bump and slab allocation, and this fine-grained async synchronization. That's the magic combination that gets them to sub-second scaling.
That's the core of the 97% overhead reduction. It makes token-level management actually work in practice.
Which, okay, brings us back to the impact. They built this thing, they optimized the heck out of it. What did it actually achieve in the real world?
The results are pretty dramatic. When they beta deployed this in Alibaba Cloud's Model Studio,
Right, a real production environment.
Aegaeon was able to handle 2 to 2.5 times more requests per second compared to the older request-level auto-scaling systems, like one called serverless LLM they compared against.
Wow, double the throughput. And how many models could they pack per GPU? You said multiplexing was maybe 2 or 3.
Aegeon was supporting up to 7 different models concurrently on a single GPU,
Yeah.
effectively doubling or more the density compared to simple multiplexing while handling dynamic load.
7 models per GPU. That starts to sound like proper pooling.
It really does. And the impact on overall hardware needs was massive. For the specific set of models they were running in the beta, dozens of them, ranging from small 1.8 billion parameter ones up to huge 72 billion parameter giants.
Yeah.
They calculated that without Aegaeon, they would have needed 11,192 GPUs.
Okay, nearly 1,200 GPUs.
With Aegaeon, they only needed 213.
213.
Yep.
That's the 82% GPU saving right there. That's incredible.
It really is. And just as importantly, the average utilization of those GPUs jumped significantly. It went from a pretty dismal range of maybe 13% to 33%,
Yeah, lots of idle time.
up to an average of 48.1%. Still room to grow, maybe, but much, much better saturation of those expensive cards.
So it really proves the value of getting down to that token level control.
Absolutely. By managing resources at that super fine granularity, they effectively sidestep the head of line blocking that plagues request level stealing. They get much closer to the efficiency you'd ideally want, like serving a single busy model, but they achieve it across a whole portfolio of diverse, sparse workloads.
Okay, so just to recap the core idea, Aegaeon's breakthrough is moving resource control down to the token level. And the only reason that's even possible is because they managed this heroic 97% reduction in the scaling overhead through really smart engineering around component reuse, memory management, and synchronization.
That's the essence of it. And zooming out slightly, the reason Aegaeon works so well in practice is that most typical user-facing applications do have SLOs, those TTFT and TBT deadlines, that provide just enough slack time, just enough buffer.
That 70 milliseconds we talked about.
Exactly. Enough buffer to hide the now sub-second overhead of switching between models. The system exploits the slack inherent in the performance requirements.
Right, which does lead to a final, maybe provocative thought for you, our listener, to consider. The research paper did show something interesting in the corner cases. In scenarios with extremely tight latency requirements, like imagine needing a time between tokens of only 20 milliseconds, leaving virtually no slack time.
Right, no buffer to hide the switch costs.
In those super strict cases, the old static approach to simple multiplexing sometimes actually performed better than Aegaeon.
Because the cost of switching, even if small, couldn't be hidden.
Exactly. So the question this raises is, as we push LLMs into more real-time safety-critical applications, things that need truly instantaneous responses with zero tolerance for variable latency, how will these sophisticated token-level management systems adapt? What's the strategy when there's simply no slack time left to exploit? Something to think about as the field keeps evolving.